Hi everyone, welcome back to Knowledge Catch. Today we shall discuss about the floating point numbers, their representation, and the IEEE 754 standard. Let's begin with a brief introduction to the reals. Reals refer to the real numbers. These numbers include all rational and irrational numbers. Rational numbers can be fractions like 1 by 2 or integers. Examples of irrational numbers are pi, root 2, and e. See the numbers on the left. These are decimal numbers. The first one I've shown the base 10. In this one I've not specified the base. In general, the numbers whose base is not specified are decimal numbers since we use them on a day-to-day basis. Consider these numbers. They have a large number of digits. There can be even numbers that can have infinite digits. To represent these numbers concisely, we have the scientific notation. Scientific notation is represented on the right hand side. This is a notation that renders numbers with a single digit to the left of the decimal point. Let us see what a normalized number is. A number in scientific notation that has no leading zeros is called a normalized number. See this number. It has no leading zeros, which means there are no zeros to the left of the decimal point. Whereas these two forms, these are not normalized since they have zeros to the left of the decimal point. These three represent the same number. First form is normalized while the other two are not. Binary numbers can also be expressed in scientific notation just as the decimal numbers. For example, this is a binary number with no leading zero. That means to the left of the decimal point, there aren't any zeros. Hence, this notation can be said to be in its normalized form. Generally, this can be expressed as shown. Since it is a binary number, the base is shown to be 2. Here, numbers are represented as a single non-zero digit to the left of the binary point. To keep a binary number in normalized form, the binary point needs to be shifted. For example, consider a number like this. It is not in its normalized form. For a number to be normalized, it should have no leading zeros. That is, to the left of the binary point, there should be only a single one and not zeros. So, in order to keep this binary number in its normalized form, its binary point is shifted to the right. So, the binary point is shifted from this position to one position to the right. And we get the normalized form like this. This means that the binary point is not fixed. It keeps floating, it keeps shifting from one position to the other. Computer arithmetic that supports such numbers in which the binary point is not fixed is called floating point. Let's now see how we can have a generalized representation for floating numbers. Consider this particular binary floating number. It has a fractional part 0.10 and the exponent. In this case, the number is positive, but negative numbers also come into the picture. Thus, a floating point number can be represented in its sign and magnitude form as shown here. That is minus 1 raised to s multiplied by f into 2 raised to e, where s is the term for the sign of the floating point number, f the fractional part, and e the exponent or the power. In this representation, when s is equal to 0, we get minus 1 raised to s equal to minus 1 raised to 0, which is equal to 1. Hence, this entire term will be positive, or the number is positive. Similarly, when s is equal to 1, we get minus 1 raised to 1, which is equal to minus 1, which when multiplied renders this term negative. The numeral 2 here represents the base of the binary number. This particular representation takes the sign and magnitude of the floating point number into account and hence the name sign and magnitude. There are multiple ways of representing floating point numbers. To improve the quality of computer arithmetic and the portability, the Institute of Electrical and Electronics Engineers, that is IEEE, 1985, developed the technical standard for the floating point arithmetic, and that is the IEEE 754 standard. The IEEE standard has two formats, namely the single precision representation and the double precision representation. In the single precision format, floating points are represented using 32 bits. That means the single precision format is a 32-bit representation of the floating points. On the other hand, the floating point numbers are represented in 64 bits in the double precision format. This is the IEEE 754 single precision format. Here, S denotes the sign of the floating point number. For positive numbers, S is equal to 0, and for negative numbers, S is equal to 1. 8 bits are allocated for the exponents, and the remaining 23 bits are allocated for the fraction. The representation of a floating point number in double precision format is as shown. Here, S denotes the sign of the number, just as in the single precision notation. Exponent takes the 11-bit field and fraction takes the 52-bit field. Double precision notation increases the exponent range, and since it uses larger number of bits, its primary advantage is greater precision.